Statistical entropy is the application of probability theory to the thermodynamic principle of entropy. It shows that entropy is a measure of the amount of disorder in a system. This fact is critical to the study of origins. Statistical entropy is based on the probability of molecular positions, which most often results from molecular motion. The tendency of entropy to increase that is seen in the second law of thermodynamics is a result of the fact that high entropy configurations are more probable than low entropy configurations. A common example is a gas in a half-plugged container. When the plug is removed, it is highly improbable that all of the gas would remain on one side. The overwhelmingly more probable situation is that the gas is evenly distributed between both halves of the container. Which is what is actually observed to occur. Entropy is directly related to probability by way of the Gibbs entropy formula. In this formula, entropy is denoted as F, K is the Boltzmann constant, and P sub I is the probability of microstate I occurring in a system fluctuation. The actual formula is minus K times the summation of P sub I times the natural logarithm of P sub I. The big problem with this formula is that it is rather hard to work with. However, these microstates are the key to understanding the relationship between entropy and disorder. Equivalent microstates are the possible arrangements of a system. The number of equivalent microstates is denoted as omega. This illustration shows the breakdown of possible microstates of a system of 6 dots. In this case, the total number of possible microstates is 64. Note that the most ordered states, of which there are 2, each have an omega of 1, with both of them having an omega of 2, such that the probability of one of them occurring is 3.12%. The next most ordered states, of which there are 12, have an omega of 12, and the probability of these arrangements are about 18.74%. And the most disordered states, of which there are 50, have an omega of 50, and the probability of these arrangements occurring are about 78.1%. This is a simple case, but it shows how disordered systems have more microstates than ordered systems do. The more disordered a system is, the larger its omega is. And the more ordered a system is, the smaller its omega is. As stated earlier, the number of possible ways for a given condition to occur is denoted as omega. In this formula, entropy is denoted as F, K is the Boltzmann constant. This results in the formula of S equals K times the natural logarithm of omega. This shows that entropy is a measure of the disorder of a system. Disordered systems have a greater number of equivalent microstates than ordered systems. The larger omega is, the more disordered the system is. Consequently, the smaller omega is, the more ordered the system is. As a result, the larger a system's entropy, the more disordered it is. And the smaller a system's entropy, the more ordered it is. The biggest problem with entropy is that it tends to increase. So what is needed to decrease entropy? A common answer is energy. That is, that applying energy to a system will decrease its entropy. However, this is an overly simplistic answer, because when energy is applied to a system, how it affects the system's entropy depends upon how the energy is applied. The best example of this is the difference between construction work and a bomb. Construction work decreases the entropy of a building under construction. A bomb on the same site with the same amount of energy will increase the site's entropy. So how energy is applied to a system affects how that energy changes the system's entropy. What is needed is a general principle that describes this difference. In conclusion, statistical thermodynamics shows that entropy is a measure of disorder. It also shows why entropy tends to increase. It also shows how and when entropy can be decreased.